This is K8BYP with I believe it's a sixth video in my series on antennas and transmission lines. After having gone through basic electrical circuit principles, including basic calculus and diff EQs, let's start to go towards the past and up to modern times. And by modern times, I mean the last 10 or 15 years. Principles that were assumed to describe antennas. These principles began in about 1860 with Maxwell, who developed equations that related electrical circuit theory to antenna fields and antenna operation. The problem is they did not describe antenna operation. What they did is equated the feed point power into a feed point with the fields around the wires, and then sum those fields up. And from that comes two things. Number one, to be able to calculate back to the input power, which is pointless because we already know that. But secondly, to calculate or approximate the directionality of the antenna, which cannot be directly inferred from the input power. Input power is just an electrical quantity. If there's a relationship, then it's something called antenna, and that does not exist in the world of circuits. Since we just came from discussing circuits and resonance, let's look at a critical historical document, The History of Electrical Resonance by Blanchard, about the 1920s, I think it was. Antennas are often described as being resonant. Someone was on 40 meters last week crowing about his 240-foot long off-center fed piece of junk that was so bad that he could only work 20 or 50 kilohertz before he had to use the tuner to pull it back in. That's a worthless antenna. But boy, did the people he was talking with crow about how good his signal was because he had an amplifier. And if you listen carefully and listen a lot, you will find there's a high correlation between those on the air in these dead band conditions with their goofed up, horrible kludge antennas, that they also must have amplifiers. And that proves their antennas are no good. Maxwell, I think, was the first to show the effect of introducing a condenser, what we now call a capacitor, into an alternating current circuit. Before this time, alternating current was entirely with inductors. They really hadn't figured capacitors out yet. Another way to put that is inductors were easy to make. They're just wire. Capacitors were a little more tricky to deal with at very high voltages. And it's very interesting to observe the circumstance. Maxwell used an induction coil for this purpose, experiments on vacuum tube discharges, and found that if you put a condenser in parallel, it was in series rather, with a primary circuit of his induction coil, he could get very much larger sparks, which meant, of course, that he got a very much larger current through his primary coil, an alternating current generator being used to feed the primary. He could not see why. And by the way, this is in the Bell System Technical Journal referred to as BSTJ. He pointed out the exact relations between the condenser, the self-induction, and the frequency which would give the largest current, and he was the first to do this as far as I know. They understood the basic nature of the R, L, and C components and values, and used that to reason out resonance. The top equation is a form that relates a series RLC circuit and calculates the instantaneous voltage on the left, E sine omega t. The t is really hard to see. That's the voltage on an instant on a sine interval, with L di dt, which is equal to voltage, R times I, which is equal to voltage, and 1 over C, the indefinite integral of I dt, which is voltage across a capacitor. Now there's an integral in there because the fundamental equation for a capacitor is not for voltage, it's for current. It's for voltage. not current. And this equation wants to relate RL and C to current, not voltage. The fundamental for the capacitor is V equals C dV dt. This equation is EE 201. It's a basic. Notice the left side relates to sine, a trig function, a circular function. That implies that di dt must also be in terms of sine. These circuits are really exponential, but we get into some really messy math if we get away from sine. Sine is so easy to integrate and deal with. The solution for the equation is blah. I is e over the square root of r squared plus omega L minus 1 over omega C squared. Omega L is the inductive reactance. 1 over omega C is the capacitive reactance. In engineering documents, they tend to work with omega L. We tend in radio to work with reactance, especially if we're looking at a certain frequency, but this is for any frequency. But what that equation implies is that I is equal to E over R, which is Ohm's law, when reactive amounts cancel. Notice it's a series circuit, omega L minus 1 over omega C. If it was parallel, it would be 1 over omega C minus omega L. But this is for a series circuit, which agrees with the equation above. But when the quantity in parentheses disappears, we get a resistive circuit, Ohm's law, from which Maxwell pointed out that the current would be a maximum when omega L equals 1 over omega C, omega being proportional to the frequency. Omega is 2 pi f, and L and C being the inductance and capacity all in their proper units. Effecting this condition would of course be a case of electrical resonance brought about by electrical tuning. That's an important term because before this they couldn't tune inductors, except to maybe make them larger. But tuning means there's a maxima. A maximum of current occurs when the parenthesis condition is 0. With an inductor, there cannot be a maxima except at infinity because it's a linear first-order system. Brought about by electrical tuning, though Maxwell himself did not specifically make use of the terms. Here's the first electrical resonance curve. See, the function comes to a peak. See, there are different shapes on either side. I mentioned this in previous videos. There are cases where resonance is very bad. We don't want stray resonances in an amplifier that causes oscillation. In these early days, they didn't really have radio. They had telephone. And resonance in telephone communication was a disaster. This is an early schematic of an early telephone system. And resonances, and especially transmission lines having differences in propagation velocity for different frequencies, led to very, very garbled communications. And in transmission lines, that's referred to as I think it's group delay or group loss, where a group of signals don't transmit down the line with the same amplitude. What's that have to do with antennas in modern days? Well, the point is that antennas either should not be or are not resonant, as I showed you from a PhD expert in a previous video. But they are universally treated as such by looking at their LC equivalents at the feed point, which is not real or not necessarily real. There are no exactly inductors or capacitors in a dipole. I mean, there are no components. A length of wire has inductance, but see, antennas work by propagating fields, not as inductors. If not, the entire length of the antenna arm would charge and discharge at the same time instead of having a pattern, because the whole of an inductor charges and discharges at the same time. There can be capacitance at a feed point, referred to as admittance. If the dipole arms sag, then there can be capacitance between the wires. But that suggests that if the antenna has capacitance because of sagging, and I've found this in experiments here, that narrows the bandwidth, and that's bad. The last thing we want is a resonant antenna, because resonance, as we just saw, implies narrow bandwidth. That C50 KC white antenna that Ham had to tune, that I just mentioned, very, very poor antenna. But even that's really not about resonance. That's about something else called traveling waves. We'll get to that later. Here is my 2-meter vertical. 1.4 to 1 SWR across the entire 2-meter band, 4 megahertz. The top trace might look generally resonant. That's the SWR curve. The bottom trace with the green, which is capacitive reactance, is absolutely not an an RC circuit. Goes to zero capacitive reactance here, capacitive reactive either side, or at least appearing to be. Dips down again, increasing apparent reactance, then goes to what might be described as a resonance. A first order LC circuit cannot do that. This is a complex antenna. It's a shunt-fed vertical. But notice, this antenna is much wider than the entire 2-meter band. Here's my 20-meter vertical. Does that look resonant at the bottom? No. Had a highly experienced EE stand in my backyard and look at this graph on the analyzer and says, I have no clue what's happening. I just laughed at it. That 20-meter vertical is almost 15 megahertz wide. There's no resonance here. So basically, forever get rid of the idea of a resonant antenna. Now let's go to another source that ARL disagrees with. Fundamentals on Electric Waves, Skilling, PhD, Stanford University. Page 169, summing up the equations, like I just mentioned, coming from Maxwell to describe the fields from an antenna. And this wonderful mythical stuff. Going on to page 170, he writes concerning the amount of fields of the antenna, the near fields, and these so-called radiated fields, which is really emission, not radiation. The myth is that antennas oscillate at sine frequencies, and that emits the electromagnetic energy, and that's absolutely false. But the induction component is negligibly small, a distance of several wavelengths from the source, for it diminishes with the square or the cube of the radius, while the radiation component that diminishes only as the first power of the radius becomes predominant. That's where the near field supposedly cuts off and the far field occurs. The radiation component represents energy that is traveling outward and never returns to the circuit from which it was sent. So the engineer and the ham say, sine wave antenna oscillates, the energy is radiated. Wrong. And that fake theory has been completely thrown in a trash can with modern physics. He clarifies that statement with, oddly enough, way back on page 107, that was page 170. When the change in magnetic field produces an electric field about a magnet, the wave of electromagnetic energy travels outward from the apparatus. And in field theory, field lines will try to go to infinity. Electrostatic lines come tangentially off or perpendicularly off a surface. They'll try to go to infinity, but they can't go to infinity without being infinitely weak, or there'd be infinite energy. It carries away from the induction accelerator of the present example so small a fraction of the total energy that it is entirely negligible. Radiation is not always negligible. In radio communication, it's a sine qua non of the practical value. The electromagnetic theory that has been developed in the preceding chapters fails to account for radiation. Those are just accounting for fields. It deals with fields that are quasi-stationary fields, changing so slowly that any instant they may be regarded as electrostatic. That's the false analogy of a dipole with a sine wave emitting. And none of that happens. And what does happen is extremely small.